Okay. All right, last three practice problems. Number 5. If a box of cargo bound for space exploration weighs 1,234 pounds on Earth, so is pound a weight or mass? Well, it's the English unit for weight. So 1,234 pounds. On Earth, what is its weight on the moon? The acceleration due to gravity on the moon, so a moon is 5.3 feet per second squared. Of course, we know a Earth is 9.8, or wait, feet per second squared, so 32 feet per second squared. And we know that we can convert to mass. Weight may change from Earth to the moon, but mass will not change. So if we convert to mass, we have one constant between the Earth and the moon. So we'll use W equals mg. We're going to find the mass on Earth because we know weight on Earth and we know acceleration due to gravity on Earth. So 1,234 pounds is the weight, is equal to mass on Earth times gravity on Earth, 32 feet per second squared. Now remember, our pounds here are really a slug times foot per second squared. So our foot per second squared is going to cancel out, leaving us with our mass unit of slugs. Mass will be 1,234 divided by 32, which is, let's see, 39 slugs. Okay, so mass will be exactly the same on the moon as it is on Earth. And I'll get rid of this little part so we can focus on the real problem, finding the weight on the moon. So the weight, we'll use the acceleration due to gravity on the moon, W equals mg. Mass, still going to be 39 slugs on the moon. Acceleration on the moon, 5.3 feet per second squared. Of course, that's straight down toward the center of the moon. We know weight is a force and needs a direction, so our answer also needs a direction. So our weight will be 39 times 5.3. Those are both two significant figures, and that'll give us 2.1 times 10 to the second, which is really 210. Either way, two significant figures, pounds, because a slug foot per second squared is a pound. And we need magnitude, unit, and direction, which is going to be down toward the center of the moon. So 210 pounds down toward the center of the moon would be our weight on the moon. Of course, since acceleration, if we look, the force, if acceleration is going to go down on the moon compared to Earth, mass, of course, is the same on the moon and the Earth. It will be constant. Then we can also see that the weight is going to go down on the moon because acceleration and force are a direct proportion, right? And we could, if we rearrange the equation, our constant mass equals force divided by acceleration. Well, we can see if acceleration goes down, then that doesn't look good at all. If acceleration goes down, then force should go down if mass is constant. It's too late. I'm going to confuse myself. Easily confused. Okay, number 6. If an astronaut weighs... Ooh, I didn't start my timer, speaking of confused. If an astronaut weighs 296 newtons on Mercury, where acceleration due to gravity is 3.95 meters per second squared, how much does she weigh on Earth? Okay, so we have a weight of 296 newtons on Mercury. We have an acceleration due to gravity on Mercury of 3.95 is it meter per second squared. How much does she weigh on Earth? Well, of course we know. What else do we know? You have to think what you know. Acceleration on Earth, 9.8 meters per second squared. So we can easily use weight on Mercury and acceleration on Mercury to find mass on Mercury. Of course, we know mass is the same no matter where you are. So then we'll know mass on Earth, and we can find whatever it wants to find, probably weight on Earth. So let's scoot this down a little bit. W equals mg. So we know acceleration due to gravity, I guess, is really g. Acceleration due to gravity on Earth is g. So weight would be 296 newtons equals mass times gravity on Mercury. Since this is our weight on Mercury, we use gravity on Mercury. It's going to be 3.95 meters per second squared. Now, when you have units like newtons that are kind of composite units, it's much easier if you say, I know a newton is a kilogram meter per second squared. So when I divide through by both sides by 3.95 meters per second squared, divide by 3.95 meters per second squared, you can see my meter per second squared is going to cancel out, leaving me with a unit of kilograms. So my mass will be 296 kilograms divided by 3.95, which is, looks like 74.9 kilograms. Okay, so that's my mass. It's the same everywhere. So mass on Mercury, 74.9 kilograms. Mass on Earth, also 74.9 kilograms. So now we'll erase, and we can use gravity on Earth and mass on Earth to tell us weight on Earth. So weight is going to be equal to mg again, of course. Mass 74.9 kilograms. Gravity 9.8 meters per second squared. Our unit, kilogram times meter divided by second squared, is a newton. So weight equals 74.9 times 9.8 newtons, which is 7.3, two significant figures because of the 7.3 times 10 to the second newton. Again, weight is a force, which is a vector quantity, so we need a direction down toward the center of the Earth because the acceleration vector, of course, due to gravity is down. So that's number 7. And one last one before I run out of time and have to post yet another video that takes 2 hours to load. Sorry, you guys have to wait till at least Wednesday because they really are slow to load right now. Number 7. Now this has something you haven't learned about, a coefficient of friction. So coefficient of friction looks like kind of this weirdo cursive U. It's a Greek letter mu. And we would call this the coefficient of friction. Now you can have a coefficient of static friction, or you can have a coefficient of kinetic friction. Of course, we said that to get something moving takes more force than to keep something moving. So the coefficient of static friction, when the thing is stationary, not moving, is always going to be greater. Well, I guess if I wrote them side by side, it'd be easier. Coefficient of static friction is always going to be greater than, I'm so bad at making those, the coefficient of kinetic friction, because it takes more force to get something moving than to keep it moving. So that's one truth that you need to know. Also, well, I'll show you the equation in a minute. They're not that hard. And I'll even show you how to find the coefficient of static friction for any two objects, as long as you can move them. We can use your phones or whatever. We did that last year, in fact. So number 7 says a 745 kilogram box. So kilogram is a mass. 745 kilogram box is sliding across the floor. The coefficient of static friction between the floor and the box is 0.45. The coefficient of kinetic friction is 0.32. Always static is larger, of course. What is the frictional force between the box and the floor? Well, it says the box is already sliding. It means it's already in motion. I only need one coefficient of friction. Since it's already in motion, I'm going to choose a coefficient of kinetic friction because the box is moving, kinetic. So I'll only write that one down because that's the only one I need. 0.32. Coefficient of friction is a unitless quantity, so I'm not just leaving off the units for fun. It really doesn't have units, and I'll even show you why soon. Can't remember when, but we'll do it. What is the frictional force? So friction, lowercase f for friction, between the box and the floor. So we have a convenient equation here. Frictional force is equal to the coefficient of friction times the normal force. the force between, what do we have, a box and the floor. The normal force is the force that opposes gravity here, this upward vector. So, what is the frictional force? Well, first I have to calculate normal force. Here, I'll put it up here. So, I need to know what that is before I can do anything. And my normal force, of course, is equal to mass times acceleration. When in doubt, go back to Newton's second law. Normal force equals mass of the box. Well, I had that. Oh, here we go. 745 kilograms times acceleration, assuming we're on Earth, 9.8 meter per second squared, due to gravity. And if we type that into our calculator, we keep two significant figures because of gravity, and we end up with 7,300 newtons, kilogram meter per second squared, as a normal force. Alright, so I'll get rid of that little piece just so we have less clutter on the little board here. Then we want to find the frictional force, which is equal to the coefficient of friction. We pick kinetic because the box is already moving. If it were stationary, we would pick static. So we're going to multiply the coefficient of friction, 0.32, times normal force, 7,300 newtons. Of course, we'll end up with a unit of Newton, which is great for a frictional force. And when I do that multiplication, I obviously both have two significant figures, only keep two significant figures. So I would find 2.3 times 10 to the third newtons to be the answer here. And we have to find a direction. Friction always opposes motion, so in opposite direction of motion. Every force is a vector quantity, and you need to have direction. So I'll see you in class. We'll go over anything you don't understand, or please feel free to give me a phone call if you are having any trouble at all. And I'll see you next week. Hope you're safe and recovering from this storm, and have a good day.